Our next speaker is Tom Luton, and he will give us an introduction to asteroid occultations.
Thank you very much, Paul. Evening, everybody. Hope you're doing well. So, as Paul said, tonight's topic is an introduction to asteroid occultations. This is a talk I've been meaning to give for a while, and when Dennis Gray did his excellent presentation last month on Occult Watcher, which is a very common piece of software we use in asteroid occultations, I figured the time was right to do this. So this is sort of a unofficial part one to Dennis's presentation. We'll put a link to it somewhere, maybe down in the comments below afterwards. But anyway, so I'm going to talk a little bit about, give a little bit of an introduction, talk about the importance of asteroid occultations in observing them in astronomy, talk a little about the history of them, give a very brief overview of how to observe, talk a little bit about discoveries, and then a little bit of my own personal history of asteroid occultation observing. So there are about 2.5 million stars that are magnitude 12 or brighter in the night sky. So stars that are within the grasp of a medium-sized amateur telescope. And as of a couple of weeks ago, there are approximately 113 million minor planets in our solar system. That's everything from the near-Earth objects that are close by, the asteroids in the main belt, all the way out to the Kuiper belt objects past Neptune. With so many stars and so many minor planets, every so often, a minor planet will pass in front of a star, blocking its light, as we see from Earth. This is called an occultation. So, this can happen at any point in the asteroid's orbit or in Earth's orbit. It's not something that only happens at certain times of year, like opposition. It doesn't rely on distance from the sun, like perihelion. Occultations are visible from anywhere on the planet, and occultations can occur at any time, day or night. Obviously, the ones that happen at 12 noon, we can't really see because the sun is out. What this means is that there's no such thing as an occultation season. They occur at random all throughout the year. There are more occultations visible in the winter because the nights are longer. So, a little bit about the importance. So, because stars are so distant from us, the photons of light from the star reach us, they're basically traveling parallel to each other. And this means that when an asteroid passes in front of a star, the shadow that it casts onto the Earth is about the same size as the asteroid itself. If you time the occultation from a specific location on Earth, and you know the speed that the asteroid is traveling at, you get the width of that part of the asteroid. Depending on the equipment that you're using, this width can be accurate to a few tens of kilometers or even to a few kilometers. If you stack multiple observations from different observers across the path of the asteroid occultation on Earth, you create a cross-sectional profile of the asteroid as it passed by. This is by far the cheapest method and the easiest method of determining an asteroid's size and shape. Large telescopes can only directly image the biggest asteroids through the use of adaptive optics, and the end result is a very blurry photo. And telescope time on the big guys is very, very expensive. Space probes are even more so. So this is one of the ways that an amateur astronomer can make a real contribution to the science of astronomy. So a little bit of the history. Lunar occultations, where the moon passes in front of a star, have been known for centuries. The earliest recorded one was in Japan in the year 640, when the moon passed in front of Aldebaran. Planetary occultations have been happening for a long time that we've known about, and we've made some very famous discoveries as a result of them. Uranus's rings were discovered via a planetary occultation of a star in 1977. As Uranus approached the star, the light from that star started blinking off and on in a regular pattern, and then as the planet departed the star, the light from the star blinked off and on in a regular pattern, except in reverse. So that's how we found the rings. Neptune's moon, Larissa, was found in 1981 through a similar method. The light from the star blinked before the planet reached it. Now, we didn't know at the time what moon this was because it was only a single point of data. We had to wait until 1989 when Voyager 2 swung by Neptune, and we got a good look at the small moons close to the planet, and we were able to then run the clock back and find out that it was Larissa that had blocked the starlight back in 1981. And we also measured Pluto's atmosphere in 1985. When a astronomical body with an atmosphere occults the star, the light doesn't just immediately blink off and blink on again. Instead, light dims and then brightens. And from that, you can measure the density of the atmosphere and learn a few other things. Now, the problem with asteroid occultations is that asteroids are a lot smaller than the moon and planets in the sky. So the small size combined with the not 100% certainty of the asteroid positions, combined with the relatively inaccurate star positions in the night sky, we didn't quite know the exact location of fainter stars to the level of precision we needed to do asteroid occultation work. It made all this early asteroid occultation observing difficult. The first asteroid occultation that was observed was by Juno, 3 Juno, in 1958. But the problem is that all this uncertainty meant that the odds of an asteroid occultation actually occurring where we thought it was going to happen weren't that great. It would be a case of the path of occultation on Earth will be here plus or minus 20,000 kilometers, for example. This uncertainty, this high risk of failure, and the high cost of telescope time meant that professional astronomers were sort of hesitant to take part, and so it fell to the amateurs to start observing occultations starting in the mid-1970s. The International Occultation and Timing Association, IOTA, was formed in 1981, and it provides information on occultations, it coordinates observing expeditions, and it collects and publishes the results of those expeditions. Occultations.org. If you get interested into this, this is one of those websites that's not only going to be something you refer to quite a bit, but it's got plenty of additional information beyond what this presentation has. Details of where you get your star charts, where you get all your additional information. So in the 40 years or so since IOTA was formed, the probabilities of observing occultations have improved greatly. We've had 2 astrometric satellite missions, Hipparchus in the 1990s and the Gaia mission, which is wrapping up shortly. And these 2 space probes have provided us with greatly improved coordinates for star positions, for stars brighter than magnitude 20. So that's basically, you're going to need some significant astronomical horsepower to get beyond the magnitude 20 point. So now most of the uncertainty for the position of an asteroid occultation comes from the asteroid itself. We don't quite know its exact orbit. However, this is one of the things that asteroid occultations helps to solve, because if we know the star's location to a high degree of accuracy and you know where you are on Earth, then, well, logically, you know exactly where the asteroid is because it's in between the 2. And so asteroid occultation observing makes asteroid occultation observing easier for the future, because knowing where an asteroid is now to a high degree of accuracy means that you'll be able to get very accurate predictions for it in the future. So, what exactly would you see through your telescope? Well, shortly before the event, about 15 minutes or so, the star and the asteroid will appear to merge and will create a single star with a combined brightness of both, much like in the same way that a double star is actually two stars so close together that you can't resolve them into two stars. They appear as a single object. During the occultation, the brightness of this combined star will instantly drop to the brightness of just the asteroid for a few seconds, depending on how wide the asteroid is that we're talking about and how fast it's moving. If the asteroid is too faint to see through your telescope, then the star will disappear completely from view. So the question that was asked in the early days was, how do you record a transient phenomenon that lasts a few seconds and then returns to normal? Well, it turns out the easiest method of recording wasn't visual, it was audio. A tape recorder with a shortwave radio tuned to one of the time signal stations on the shortwave is set up, and the observer looks through his telescope. He observes the asteroid disappearing and reappearing, and every time and when it disappears, traditionally you call out "gone," and when it reappears, you call out "back." And these words are picked up by the tape recorder. We use "gone" and "back" because they're words that have a strong consonant at the front and a very strong start to the word. Then the morning after, you take your recording, you replay it with a stopwatch to get the exact start time, end time, and the duration based on the distance between the two. More modern, it's a little easier because we've all got smartphones these days with recording features in them. You simply, instead of a tape recorder, you record with your phone, and then you can use some of the software in your dictation or your recording app to slow down the recording so that you will be able to get the time of the time of the disappearance and the reappearance to a very small fraction of a second, actually. So yes, this does introduce errors due to the human response time and human reaction. With practice, that will get down to about, you'll be accurate to about 0.3 of a second, but there's a bit of a learning curve. Just one note, you cannot use an internet-based time signal for this. You need a shortwave radio. The reason being is that the data routing adds random milliseconds to the internet time signals that you might get off the internet, and as a result, that's not good enough for what we're trying to do here. So we've tried using photographic time-lapse in telescopes without tracking. And it has worked in a few cases, but usually it was too technically challenging to set up, and the cost of film in the time period made it impractical. So what happened was we started using video cameras in the 1980s, mounted on their own tripod, pointed at the eyepiece. And then as the video cameras got smaller and smaller, by the 1990s, we were attaching them to the eyepiece, and by the early 2000s, we were using them instead of an eyepiece as webcams got fairly small. And this is getting a little beyond what you'd want. The equipment requirements for these are a little beyond this presentation. But if you're interested, after a few attempts with some of the simpler methods, again, occultations.org will have all the details you'll need. As to what kind of equipment for a telescope, any size will work. But the bigger the telescope, the fainter the stars that you're able to see, and therefore the more occultations you'll have a chance to take part in. For example, I use an 8-inch, and here in Southern Ontario with moderate light pollution, you'll get past 12th magnitude, but not a huge far past 12th magnitude. I use a Dobsonian, but I would recommend, if you can, to use a telescope that's got a tracking mount. The reason being is that you can find the star, and then if a cloud happens to move in and then move out with about 10 seconds left to go before the occultation is expected to start, you can still observe it, and you don't have to worry about trying to reacquire the star because the field of view has shifted. And so this kind of gives you the hint of what can go wrong in one of these. I mean, at first glance, it sounds fairly simple. You get your data beforehand. You get your little star chart. You find the star, either star hopping or just punch in the RA index, and then you just wait, right? So the problem here is that we've got a ticking clock. Asteroid occultations are unlike almost anything else in astronomy in that you're dealing with an event that it only lasts a few seconds. If you've ever done anything regarding a solar eclipse, you know how fast a few minutes can fly by. This is even worse. And that ticking clock means that what normally would be a complete, nothing to even worry about event with your equipment turns into something that will completely wreck the observing session. For example, the radio time signal can go completely into static because the ionosphere decides to have a seizure. Your batteries can die, especially in cold weather. Your eyepiece can fog up at the absolute worst moment. As I said earlier, clouds can be a problem because patchy cloud, well, in a normal night, you would just wait until that one cloud moved out of the way of your view of M13. But now that one patch of cloud happens to be there at the exact wrong moment. And remember I said these things can happen randomly? Well, that means that they can occur at 3:30 in the morning. And if you're one of those people whose morning ritual requires about 2 hours and 3 cups of black coffee to get going, you might want to consider skipping the events that take place, in the wee hours. Anyway, when things go right, you get this. What you're looking at is the result of an expedition by IOTA in July of 2011. This is the binary asteroid Antiope. Every single one of these colored lines is somebody's observations, and we've got a few dozen of them. So what you're seeing here is this is a binary asteroid. It's not one asteroid seen twice. This asteroid is actually made up of 2 rocks, and the rocks orbit each other as they go around the sun. So, I mean, this describes it perfectly. What we've got here are 2 lumps, each one about 75 kilometers in diameter. You can see the top one is sort of egg-shaped, and the bottom one has a nice chunk missing out of the side. So some of the things that we have found as a result of asteroid occultations is we found new double stars, because what will happen during an occultation, if the star being occulted is a double star, is that the light from the star will not completely disappear all at once. It'll drop out in steps as one star is occulted, and then a fraction of a second later, the second one is. And the same thing with the reappearance. It'll reappear in steps. We have also had, in addition to binary asteroids like you've just seen, we've had the discovery of satellites around asteroids, which our own Guy Nason has described as satelloids. So we actually started finding these before the scientific community did. The amateurs found them. The problem was that at the time we didn't have recordings of the actual occultation. We just had the audio recordings. So there was no hard proof. And at the time there was still some uncertainty as to whether or not an asteroid could have a satellite. We didn't have proof of that until Galileo flew by 243 Ida in 1993 and imaged the asteroid and its satellite. And since then, we've found a few more. So a little bit about my history of asteroid occultations. I've been doing this since 2005. In that time, I have attempted 51 different occultations. 21 of them were failures, as in I set up the telescope, but something went wrong. Now there's a learning curve when you start out with this. You discover things like, okay, this star was too faint, so I shouldn't have tried in the first place. Okay, I'm a little too close to sunset. I'm a little too close to sunrise. So all I've got is blue sky. I've got is dark blue sky in my field of view. Some equipment problems, a few clouds, but it's all part of the learning process. I've had 25 misses, 4 of which were closest recorded misses. I'm going to talk about missed observations in a moment because they're actually rather important to this. And you will want to even set up your telescope in locations where you know or where you hope the asteroid won't be. And I've had 5 successes where the asteroid, I set up a telescope and the asteroid did exactly what it was supposed to do and the star blinked. So this is an example of why misses are important. This is the occultation by asteroid 346 Hermantaria in October of 2014. What we have here is the work of 3 members of the Toronto Centre, myself, who my observation is the purple line down at the bottom. Above that is Guy Nason, and then the pale blue line at the top is Dennis Gray. The dotted line was the predicted center line. So this asteroid looks like it shifted southward a little bit. And the reason why misses are important, it shows up beautifully in this image, because it tells by having misses occur, having observers miss the asteroid, we can confirm that the asteroid is not larger than expected. I mean, the circle here is a circle of best fit. But the asteroid most likely does not look like a perfect circle, 101 kilometers in diameter. In fact, it's possible that what Guy picked up was a cigar-shaped asteroid seen from the side. And so the asteroid is nowhere near 101 kilometers in diameter north-south. But because of Dennis's observations and my observations, we've got a maximum size, which is helpful. Here's another example. This is 1030 Vitya's occultation on April 28th, 2012. Again, the dotted line was the predicted centerline path, and you can see that that's where most of the observers were centered on. I'm the one pale blue line up in the upper left. And what you see here is the asteroid shifted northwards. So we got a lot of people on the north side of the path, some of whom, if you compare the size of the estimated asteroid size to the path center line, if that asteroid hadn't shifted, some folks like Brad or even Paul Markov here, who's the pale blue line below the red one, number 3 here, would have actually missed. But instead, because they were set up on the outer edge of the predicted path, and the asteroid shifted in position, they were able to contribute quite a bit of information. This one was a big effort by the Toronto Centre. In addition to myself and Paul Markov, there's Eric Briggs and Patrick McDonald and Dennis Dray who contributed to this. And this is what I was talking about when I said observers scattered along the observation path. The green line was the predicted center line, and the blue lines represent sort of okay, we think the asteroid is this big, and we're trying to confirm it. But so green center line is the center line. Blue lines are supposed to be the edges of the asteroid, but remember, this thing might shift. So the red lines on the chart are statistically calculated lines showing that this is the 1 sigma deviation. In short, if you've taken some some statistics courses, the probability that the asteroid would be between those red lines was 68%. So the idea is to spread a few people out on either side of the blue lines in case this thing moves. And you can see we had good coverage here in Southern Ontario and then a few other folks in New York State. This is a more recent occultation. This is by 375 Ursula in August of last year. I'm number 5, the brown line just above the dotted line. And you see here, in this case, the yellow circle is a fairly decent fit. But one thing I discovered is that there's a good-sized chunk missing out of the south side of this asteroid. So if this talk has gotten you interested and you'd actually like to try one asteroid occultation without any of the pressure of actually observing it and trying to get some real science, what we got one coming up in a few weeks. On Monday, November 1st at 7:52 p.m., asteroid 4082 Swan will occult a 10th magnitude star in Triangulum. The link is to the IOTA page with the relevant information. The predicted path of this occultation runs over Belleville and Prince Edward County in eastern Ontario. So that's far enough from the GTA that a miss here is likely. So you don't have to worry if you want to try it here in the GTA. The odds of you not seeing this are pretty good. But try it again. Try it anyway to get a sense of the pressure and what you're trying to do when you've got a clock ticking. And of course, to go along with what Dennis was saying last month, download Occult Watcher so you can get the full details, such as the to the second occultation time and access to some of the tools and so forth. And with that, I'd like to wish you good luck, and I hope you take a stab at least a couple of asteroid occultations. And does anyone have any questions?
Thanks, Tom. Great presentation. Very interesting topic, at least it is to me, because I have done 2 or 3 occultations in the past. I'd like to try some more in the future. Do we have any questions, Emma, for Tom?
We do. We have a few questions. The first one comes in from Louise. Right now, the sun and the new moon are in the sky, very close. Which one appears faster on any given day?
Didn't we just have this question?
It was a bit different. It was asked twice, though.
Mm-hmm.
So, so we'll repeat that, please.
The sun and the new moon are in the sky. Which one appears faster on any given day?
The moon should appear faster because it makes a complete circuit of the sky in 29 and a half days.
Thank you. Is there a way to use GPS signals for the time signal?
I've only ever used a shortwave. I've never used a GPS time signal. I think so. You'll want to take a detailed look into IOTA's page to see if there is I believe there is a procedure for doing that. Check with IOTA's page. They'll have the details on that.
Thank you. Our last question. Is a minor planet an exoplanet or a planet in our galaxy?
Okay, a minor planet is, to put it bluntly, something that is smaller than a planet. So we're talking something generally, it's in our solar system, asteroids and Kuiper belt objects, the largest of which, if I recall correctly, maxes out at about 3,000 kilometers in diameter. Other solar systems are more than likely to have their own collections of minor planets. And so, but those are so far away and so small and dim that we won't be seeing them until we start getting a working warp drive.
Thank you. That's all the questions.
Hey, Tom, I actually just thought of a question myself. I'm going to go ahead and ask it directly. Typically, I have trouble with my shortwave radio obtaining a signal consistently. Often the signal is hard to hear. It comes and goes. Any advice on how to pull in a better signal?
Okay, so my first comment is there are several frequencies that the time signals are being transmitted on. The Americans transmit on, I think it's 6 different frequencies, and the Canadians on 3, all of which can be picked up with shortwave radio here in Southern Ontario. In my experience, the first thing you do is before the occultation happens is you cycle through all of the frequencies just to find the one that's the clearest. And usually you'll be able to keep that one all right. And then what you should also do in your shortwave radio is have those frequencies pre-programmed so you can flip from one to another very quickly simply by just pushing a single button. So there are some tricks with respect to, say, longer antenna. Some folks will get some copper wire, wrap that around the antenna, and then lay that down on the ground to get a longer baseline antenna. But generally speaking, also, one thing is that when the ionosphere does decide to go nuts, and usually it's short term, so one option is to simply leave the shortwave and the recording device on for after the occultation, because eventually it should clear up and you should be able to get a steady time signal again. And then what you would just do is you would work backwards from that time signal at the end of your recording.
Okay, good. Thank you very much, Tom.